I'm clicking it and we are live.
Good afternoon, everybody. Welcome to the second annual Senior Capstone Film Festival for the William E. Boeing Department of Aeronautics and Astronautics. We thank you all for taking time to join us in celebration of our seniors' achievements in engineering, teamwork, and design. It is my pleasure to introduce our MC for today's event, advanced PhD candidate, accomplished researcher, beloved teaching assistant, and all-around outstanding member of the A&A department community, Mr. Daniel Cruz. Danny, take it away.
Hello, I'm your MC, Danny Cruz, local hot glue enthusiast and 100th year PhD student. Okay, maybe not that long. With that, welcome to the second annual Film Fest, Capstone Film Fest. We've got a whole bunch of awesome videos lined up for you today. But before we get started, I'd like to introduce Professor Christy Morganson, chair of the A&A department, who's going to deliver some remarks about the program today.
Thank you. Hello, graduating students. Hello, family, friends, and alumni. Even as we gather virtually, I would like to acknowledge the Coast Salish peoples of this land on which we gather, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. We respectfully acknowledge their stewardship of this land throughout the generations. What a year. It is probably safe to say we're all ready to move on from the status quo of this past year, but I think there is value in reflecting a bit on some of the adjustments that we've had to make that are better than what we've been doing before. We've had to be imaginative in problem solving, communicating with each other, and connecting. This Film Fest arose out of that imagination last year. And as a vehicle to connect us, students, faculty, staff, alumni, family, and friends, it was extremely successful and fun. We in the A&A community get to be treated to your imaginations. We are sending you off into your careers with technical expertise, and now we see deeper aspects of your capabilities and creativity. I would like to point out by saying that last year's capstone teams had to do a lot of pivoting as our in-person teamwork suddenly halted, and we had to adjust our prototyping deliveries. But this year, you all got it done. You entered this year with a clear understanding of how to work under these conditions. You're delivering your prototypes while still primarily working remotely. These are skills that will serve you very well going forward. So while this was not the college experience you had hoped for, there is value in its experience. And this evening, we are going to enjoy this time together. We have gathered our sponsors, alumni, faculty, staff, and families to celebrate your efforts, contributions, creativity, and innovations. We also have some alumni joining us today. I would like to offer a special note of thanks to our alumni judges panel for volunteering their time to determine the alumni's choice and honorable mention awards. These individuals will be judging the films on criteria such as accuracy, uniqueness, professionalism, and the potential impact these capstone projects will have on our industry and society at large. The members of our judges panel include Eleanor Forbes, Eduardo Gonzalez Vega, Heather Ross, Mike Taniguchi, Jim Teslow, Todd Thompson, and Rao Varanasi. Thank you all for volunteering your time to support this activity and our students. I'd also like to give a big thank you to our TAs, Nick Mavriplis and Andrew Jansen, who have really worked hard with all of the teams. I would now like to introduce Kurosh Hadi to make a few remarks. Kurosh is a very special friend of the department. He is the 2020 Distinguished Alumnus. His ties to the department began as an undergraduate when he also worked at the Kirsten Wind Tunnel student crew. He then received his MS from the department. Before retiring last year, he was director of product development at Boeing for many years. For the A&A department, he was the Boeing executive focal and served on our visiting committee. We are so glad to have Kurosh here with us, and he has a few words for the senior class. Kurosh, I'll pass it off to you.
Great. Thank you so much, Christy, for the introduction and for the invitation for me to join this outstanding event. I want to start with basically congratulating the class and what a senior year you guys had. So during this pandemic, I want to really congratulate your last year, especially. Wish I could be in person and all of us to be on that beautiful campus, but we do the best we can, and maybe sometime in the future I get to meet all of you in person. You guys had outstanding achievements. Should be very, very proud for completing this outstanding degree from a very top program, which is the only one in the Northwest and very well perceived in the industry. You're going to have great memories along the way. You're going to have some exciting times ahead. Some of you are going to work on space stations, space travel, rockets, airplanes, supersonics, environmental friendly airplanes, such as electric airplanes, autonomous aircraft. So there's a lot of exciting projects ahead of you. And one of the important things that I really want to emphasize is your continuous learning and your teamwork. So you did some of that in your capstone projects, which are exemplary work. And I'm sure that you'll get graded really well by all those outstanding judges. And the work that's basically project-based engineering and project-based learning and teamwork had to be really done throughout your design projects. Great examples of the teamwork, design, and analysis would be very clear throughout your projects. And you're going to use some of that not only in the near future, but throughout your careers. You'll come across some projects that requires really a lot of teamwork. Some of you are going to go work as propulsion engineers, structures, systems, avionics, controls. And along the way, you're going to be on teams that you have to work very closely with finance, communication, sales, customers. So you really need a lot of cross-functional coordination. So I encourage you to really go after that. Communicate regularly with everybody, especially your customers. So remember that, communicate. You can never communicate enough. And a lot of this project-based engineering, as you know from your design projects, starts with the requirements, really understanding your requirements well. Have good project plans in place. It's not just about the design and analysis. Those are really important, but it really helps your project management with having those. And at the end, don't forget that not everything will go right and according per the plan. So make sure you have your risk mitigation plans, including risk for cost, schedules, performance. Have some buffers in mind for those. And look at those in detail. So at the end, I want to welcome you to an exciting industry and the workforce. Look for opportunities, look for continuous learning, find mentors and take advantage of those. And you're going to have very many successful teams, projects, and accomplishments waiting for you in your near future. Congratulations.
Thanks, Karosh. This film fest is live, and so anyone watching at home, you'll be able to vote in the People's Choice Awards as well, so we can see what the popular vote is for the for these videos. So you can find the voting ballot. It should be in the YouTube description, also at the top of the chat window on YouTube. So if you see anything that you like or enjoy, or just whatever comes to mind, go ahead and put that up on the YouTube comments so we can know that you're watching and that you're here. So also, everyone who's viewing can vote. So it doesn't matter where you are. The people's choice. So now I think it's about time to get started with our videos. So first up, we have the Applewhite Baton. So this UAV project is essentially a sort of a flying capsule that can be used to deliver supplies in search and rescue. So let's see what we've got.
We are the Applewhite Baton Capstone team, consisting of 6 students specializing across several subteams: structures, propulsion, payload, aerodynamics, avionics, guidance, navigation and control, flight testing, and safety. We are advised by Dr. Morganson, and our industry mentor is Paul Applewhite, CEO of Applewhite Aero. The Applewhite Baton is a precision delivery system designed to be dropped both out of a manned helicopter or aircraft and also an unmanned UAV system. With its small profile as a result of its coaxial copter design, rather than the traditional quadcopter design, which takes up more surface area, The Baton is designed to be a hard-to-hit, fast-moving target. It is designed to be dropped out of a moving vehicle and fly autonomously to a pre-programmed target destination using GPS and onboard sensors to stabilize and provide real-time position, acceleration, and altitude readouts. Due to its small profile, one of the many applications of the Baton is precision delivery of medical supplies or critical equipment to soldiers on the ground in hostile conditions. However, the Baton can also be used in search and rescue applications, as it is designed to carry an audio package with a communication system payload to help locate lost hikers or children. The impacts of this device are huge. Currently, the Baton is a very niche device with its slender profile and coaxial propeller design. Furthermore, coaxial copters themselves are rare to see due to tight margins for stability. So far, the NASA Ingenuity Mars Copter and KA-52 Alligator are some of the few coaxial designs present in industry. Work done on the stability analysis of this profile is likely to be fairly novel, as there are few designs that currently utilize this setup. Thus, advancements made on the Baton also advance our knowledge about coaxial systems. This team has made several improvements to the Baton. First, several structural components were improved by redesigning connection mechanisms to ensure the Baton's stability during flight. The GPS and other modules were moved to reduce interference issues. Propulsion testing was conducted to select a battery capable of supporting the aerial delivery mission's duration. A GNC program was designed to be compatible with the autonomous flight software. This was developed from scratch using the MATLAB UAV toolbox. The team is currently flight testing the Baton while making further improvements on the GNC algorithm in the process. There are also a few integration issues that have developed, and the team is working hard to get those resolved before moving on to drop testing of the device off of a moving UAV. Thank you for watching the Applewhite Baton project.
All right, that was awesome. Looks about the perfect size to deliver me some cookie dough. So, all right. So just FYI. So next up, we've got the Boeing Disaster Response UAV. So these drones will be able to provide real-time wildfire and natural disaster observations. So let's roll it.
Hello everyone, and welcome to the Boeing Disaster Response UAV project. My name is Howard Pang, the Chief Engineer / Project Manager for the team, and I will be introducing a bit of what we've done over the course of these 2 quarters. This year, we are providing the conceptual design for a high-endurance UAV capable of carrying cameras and a payload system that provides cell coverage to an operation area. But first, let's discuss why we're doing this. As a result of ongoing climate change, the scope, intensity, and frequency of environmental disasters has been steadily increasing in recent years. When responding to such events, crews are hampered by 1. A lack of situational awareness due to the large scope of the disaster, and 2. A lack of reliable communications due to damaged and destroyed infrastructure. This UAV aims to mitigate those issues by providing situational awareness via its camera system and communication support by acting as a flying cell tower. This will hopefully reduce injuries and death during disasters by giving responders the capability to act faster and with better information. For the project, the team used an iterative design process where a preliminary model of an aircraft was first designed using estimates from existing systems. Then, subsystems were refined and details were added and checked against the overall aircraft. This process was repeated until there was a detailed final design.
Our aircraft was primarily modeled in OpenVSP. This is a program that allows us to parametrically design our aircraft and modify it easily during our design process. Important aircraft parameters, such as the wing area, were determined using traditional aircraft sizing equations. OpenVSP also allows us to modify other aspects of the aircraft, such as our control surface areas, deflections, and positions. The included Vortex lattice code helped us calculate and determine all of our coefficients, as well as all of our stability derivatives.
The Disaster Response UAV has a max takeoff weight of 722 pounds and a 25-foot wingspan. With 225 pounds of fuel, the turbocharged Rotax 582 with a 63-inch variable pitch propeller provides a max endurance of 13.5 hours at 120 knot cruise. If needed, the UAV is capable of 192 knot dash speed and has a service ceiling of 23,000 feet. The UAV is easily deployable with a 536-foot takeoff distance and a 525-foot landing distance. A hydrogen fuel cell provides 800 continuous watts of power to the payload and control systems. Mounted underneath the nose of the UAV is a sealed and stabilized camera gimbal with an infrared thermal imager, HD video, and a laser rangefinder with an integrated high-precision GPS. Atmospheric sensors within the fuselage provide important data to personnel on the ground. Lastly, a mobile cell phone satellite provides first responders and people in the affected area with a 15-mile radius of LTE service.
All right, nice work, everyone. Yeah, which end of that points forward? I'm just kidding. All right, so next video, we have Aero Environments UAV. So if you like drones, you're in for a treat with this one because this team launches drones from their drones. All right, let's roll it.
Hello, everyone. Our sponsor, the Aero Environment Company, seeks to understand the feasibility and challenges associated with deploying one or more small UAVs from the bay of their Puma-class battlefield reconnaissance aircraft. This capability, once fully developed, will be a significant force multiplier, allowing infantry personnel to scout and survey a variety of targets from relative safety. Our role in this process is to develop a prototype micro UAV, control algorithm, and deployment system for integration into a large RC plane. Once complete, we will conduct full-scale flight experiments to demonstrate the concept.
All right, nice work, team. That was great. So, so next we have exploring SAR-sustaining cosmic flows of tenuous plasma in the distant universe. We have the Meritus mission. Roll it.
Hello, we're the 6U CubeSat team, and we are working to observe the richly dynamic gases flowing around and throughout galaxies known as the circumgalactic medium, or CGM. These gases play an important role in the formation of stars and galaxies. Currently, nobody really knows what the CGM looks like or how it behaves. We plan to change this. We will measure the presence of specific gases around various galaxies. To do this, we are building Meritus, a 6U CubeSat. With the measurements from Meritus, we hope to help answer the specific question, how do galaxies receive the fuel they need to create stars? It starts with the payload, a 3U by 1U Cassegrain style telescope. The payload uses 2 concave mirrors and 6 filters to collect light in the far UV range to observe the circumgalactic medium. It uses a microchannel plate detector, an instrument that allows a nearly constant tracking of photons coming into the telescope from the galaxies we're observing. With this telescope, we can achieve detailed images of faraway galaxies, and the longer we can observe them, the better we'll be able to understand the circumgalactic medium. To hold the telescope and all other components, a machined aluminum chassis will be built. But first, a 3D printed prototype will be used to make decisions on how components fit and are arranged inside the spacecraft. The chassis is made up of 5 pieces and has been designed to withstand the loads and vibrations that Meritus will experience during launch. Along with mounting hardware, this chassis forms the backbone of the spacecraft for all other components to be secured to. In order to communicate with Earth, the spacecraft has to be within range of the UW ground station. While in range, it reorients to point the S-band antenna at the ground station, receives any commands we might send it, then transmits any data it has collected during the mission back down. The key design considerations that were looked at when choosing an orbit were communication bandwidth, communication time, eclipse length, and time in the sun. Lower orbits provided greater bandwidth but lesser communication time. The converse was true for higher orbits. Ultimately, an orbit that balanced communication time and bandwidth was chosen for optimum performance. This decision was verified by visualizing the orbits and using simulations. For this mission, the pointing determination of the spacecraft must be very accurate. Star trackers, magnetometers, and magnetorquers will be utilized to meet this requirement. Magnetometers can measure the Earth's magnetic field and use this information to determine the spacecraft's orientation with respect to the Earth, and magnetorquers create their own magnetic field that can interact with that of the Earth to reorient the spacecraft. Star trackers determine the orientation of the spacecraft by identifying stars in its view and measuring the separation angles between them. The electrical power system manages all power generation, use, and storage on the spacecraft. While in sunlight, the EPS is able to power the spacecraft with solar panels alone, and all extra power goes to charging the batteries. While in eclipse, the batteries power the spacecraft. The batteries are sized to store significantly more than the required energy in order to maintain their health for the duration of the mission. With all these subsystems working together, the Meritus spacecraft will help discover how galaxies are formed and what's happening behind the scenes of the circumgalactic medium. We would like to extend our thanks to our advisors Charlie Kelly and Taylor Reynolds, as well as our stakeholder, Sarah Tuttle, for the help and guidance throughout the design process, and optical engineer Cal Cadleck for designing the telescope.
Much mystery. Thank you, Meritus. All right, so this next team's project is very rotational. That's harder than it sounds. Let's see what they've got.
Hi, welcome to the Sockeye GNC hardware capstone. My name is Branton, and today we're going to show you what goes into the GNC system of a CubeSat. Here at AACT, or the Aeronautics and Astronautics CubeSat team, we want your satellite control to run as smoothly as possible. That is why we have aspired to deliver an optimal solution to the average consumer's satellite control needs. We combine flight-proven, off-the-shelf sensors and actuators with custom-developed flight code to give your satellite an attitude adjustment.
Our team is comprised of 4 GNC engineers, myself, Alex Chen, Brandon Bradford, Will Paul, and Ryan Laureate. In conglomeration with our faculty advisor, Charlie Kelly, and our industry mentor, Taylor Reynolds. Our GNC control system will be flown on the satellite for optimal control and imaging, aka Sockeye, which is a small CubeSat being built by about 50 students here at University of Washington. Sockeye is scheduled to launch to orbit in April 2022 aboard the Firefly Alpha rocket. Now let's take a look at our project and how it fits into the Sockeye mission.
Here's a gyroscope test unit which will measure the satellite's angular rates. As gyroscopes use the principle of angular momentum, they will measure the rotation in all three axes as demonstrated here. The satellite will need to sense the sun's location to charge its power system via solar panels. To do this, it uses a sun sensor which is seen on a custom-built test stand. Here you can see the apparatus measuring the sun vector in a sun simulator. The photodiode will be used as a secondary sun locator in the case of the sun sensor's failure. A sample plot is shown here with the idea being more current is generated when light is received. A set of 4 reaction wheels act as the satellite's primary actuator, orienting the satellite in necessary directions. Here we have a hardware in the loop testbed which is used to illustrate the flight system's validity.
So this is a full-scale model of Sockeye that we 3D printed. So some big features on here. We have the camera at the bottom. We have our main actuator, the reaction wheels right here. And then most of our sensors are actually going to be on a board in the middle. But we also are going to have a sun sensor on one of the outside faces. So in orbit, all these spaces will be covered by solar panels, and we'll have an antenna that comes up top.
Here's a quick demonstration of the satellite reorienting itself to image a target on Earth.
Well, that about covers our work here on the Sockeye GNC hardware capstone. Our project has demonstrated budget-friendly methods to design and test spaceflight hardware, opening the door for more groups to put stuff in space. We're looking forward to our launch in April, and we can't wait to share our mission results with you. Thank you.
Well, thanks for guiding us to a new understanding, Sockeye. All right, so for our next video, we have leading us towards efficient supersonic passenger travel, Scaleless. Let's roll it.
Here at the University of Washington, we are extending the bridge of supersonic travel to you through our NASA Scaleless passenger jet. We strive to make air travel faster than current commercial airliners, while also increasing the efficiency and passenger comfort compared to previous commercial supersonic airliners such as the TU-144 and the Concorde. Partnering with the University of Michigan and Stanford, our team at the UW consists of 13 students and 2 advisors, with sub-teams focusing on aerodynamics, propulsion, CAD, simulations, and integration. Previous supersonic airliners, such as the aforementioned Concorde, gave insight to the new frontier of supersonic commercial flight. The Concorde allowed travel from Paris to New York in just 3 hours, much faster than any airliner currently in service. Concorde tickets were very expensive and didn't offer a very comfortable experience for passengers. The seats were narrow and the overhead space was tight. In addition to the sonic boom, the Concorde's afterburners create a deafening jet noise and significant fuel consumption. These are just a couple of the issues with supersonic airliners that the Scaleless design works to fix.
The NASA Scaleless design has been a continuous effort of students and industry professionals for over a decade. The 2021 team built on and validated the efforts through an iterative design process using a variety of performance indicator tools such as OpenVSP, DATCOM, AED-Sys, and wind tunnel tests. Our design process all starts with the integration team. This team has created an extreme mission performance code that spits out a detailed time history analysis of fuel consumption, weights, and range. The information is handed off to the CAD team, who not only makes important changes to the overall geometry, they more clearly define the airliner, adding an interior with seating arrangements, storage space, an environmental control system, and landing gear. After making these changes, the CAD team hands the model off to propulsion and aerodynamics, who compute necessary performance inputs for the mission performance profile based off of that geometry. Furthermore, the aerodynamics team is combing through hundreds of Kirsten wind tunnel tests that were done in the summer of 2020, making sure configuration is the best one for the mission. The 2021 Capstone team has also made a few improvements to the 3x3 wind tunnel flow visualization capabilities, including new laser sheet and an advanced smoke tubing system. These improvements will allow for future Scaleless teams to continue high-quality wind tunnel testing. The Scaleless project is just one of the many cogs that will contribute to the development of future supersonic aircrafts, and as the price of fossil fuels rises, the demand for more efficient travel has never been higher. We look to impact the aerospace industry by creating a non-proprietary configuration that can be used by companies, since there are very few supersonic aircraft resources for low-speed performance. We believe creating this resource base can help grow the supersonic airliner market to soaring heights. The coronavirus pandemic tore the world apart, forcing lockdowns, isolating families, and mandating quarantines. But now it's time to break these barriers and bring the world back faster than ever before.
Well, that's just super, Scaleless. Okay, no, nice work though. All right, so for our next video, we have SARP, Society for Advanced Rocket Propulsion. So this year's SARP propulsion project put the advanced in Society for Advanced Rocket Propulsion with their Aerospike nozzle design. Let's see how it went.
SARP is a student-led organization at the University of Washington with the continual goal of technical excellence and achievement through rocket science. Part of the senior team's job as SARP Propulsion Capstone is to research and develop new technologies that are useful for future achievements and research. Hence, we give you the Aerospike. The Aerospike nozzle is a specific type of nozzle which improves fuel efficiency in low altitudes. Its unique shape means that we can achieve optimal pressure ratios and therefore decrease fuel consumption. With our faculty advisor, Professor Jim Hermanson, and industry advisor from Blue Origin, systems engineer, Ms. Nissa Thompson, SARP Propulsion has worked months on designing a small-scale aerospike capable of 70 pounds of thrust using gaseous methane and air for propellants. Since aerospikes are currently not being flown, designing a working spike would be a success in itself. So, how do we do that? It started with sketches and analysis of trade studies. We added an additional challenge of attempting to gimbal the Aerospike nozzle and designed a fluid injection system to complete this new system requirement post-trade study analysis. Heat transfer, a major driving factor in the Aerospike, was completed and updated throughout the project with support of MATLAB analysis. Subsequent initial CAD designs were then created as we worked on designing each component. Over time, our design evolved as our analysis deepened and our design improved. From mass flow calculations to fluid injections, PNID diagrams, and electronic diagrams, we worked on completed system integration. Once we had our design, we faced our biggest hurdles: assembly and manufacturing. Slowly but surely, the pieces came together, while the fluid injection design is being saved for future projects. The Aerospike has various impacts in society. Technical impacts include learning more about aerospikes and improving our basis of understanding. Increasing research in this area gets us closer to industrial and commercial use. Economically and socially, aerospikes play a role in industrial decisions. Initially, aerospikes will not be inexpensive to put into practical use, but with successful use, they decrease needed fuel and therefore decrease price in the long term. Social impacts are closely tied with economic impacts. With increased fuel efficiency, spaceflight becomes increasingly accessible. Environmental impacts are similar to any rocket nozzle, but are especially low with our design. We expect minimal impacts because our fuel is gaseous methane and air, and our analysis confirms we expect low carbon monoxide emissions. SARP, increasing spaceflight and reaching for the stars.
All right, thanks, propulsion team. That thing's spiky. Careful where you point that thing. Okay, so coming up with a second SARP video here, we have the structures team continuing a long tradition of innovation. This year's SARP structures project converted one of the more complex structural components into a novel carbon fiber percussion instrument. Let's see how it went.
We are the Society for Advanced Rocket Propulsion, otherwise known as SARP, a student-led organization at the University of Washington that designs, builds, tests, and launches a rocket for competition each year. As a team, we've been pushing the boundaries of collegiate rocketry since 2012, and we are aiming to reach the edge of space with a rocket by 2025. When reaching for space, every ounce counts. More mass means more that the Earth's gravity holds our rocket back. To this extent, given our current propulsion system, every pound of weight that we shave off yields us 100 feet of higher apogee. One way to cut back on weight is to use materials with high strength to weight ratios, such as carbon fiber.
Our Capstone team pursued an R&D carbon fiber coupler, and we are planning to have a similar part replace the weighty all-aluminum design that SARP has used for the past 6 years. This part, known as the recovery coupler, serves as the hard point during parachute deployment and has to withstand the shock loads delivered by the parachutes, as well as the thrust and acceleration generated by launch of the rocket engine. By switching the material to a carbon fiber, we utilize the material's strengths, keep the original functionality of the recovery coupler, save weight, and thus increase apogee. This design was optimized using analysis ran in ANSYS ACP, a composite analysis software that reassures the practicality and safety of the design. The carbon coupler weighs 48% of the aluminum alternative and will give the rocket an additional 240 feet in altitude.
This coupler is also enhancing SARP's baseline of composite manufacturing skills. The coupler needed a new mandrel, an aluminum mold that plies of carbon fiber were placed over to create the part. The mandrel was manufactured in-house by the team in a precision machine shop and consists of two pieces, a tube and bulkhead that bolt together. The mandrel was treated with chemicals to seal the surface and prevent the coupler from sticking to it, giving the coupler a superior surface finish. Our manufacturing process has been optimized through multiple practice layups that proved the repeatability and reliability of the process. To manufacture the coupler, the mandrel was rolled over carbon plies and then folded over the top, in a pattern that enhances the strength and reduces the safety risks normally associated with carbon fiber.
The coupler is currently in post-processing and will go through testing by the end of the development period. These tests will ensure that it withstands the associated loads in real life, not just in simulations, and repeated loading will demonstrate the reliability of the design. The part is not only impressive in the context of student-developed rocketry, the geometry is complex, so our design and associated processes are substantial even in the realm of aerospace. Composites like carbon fiber and fiberglass are being utilized more and more in aerospace as well, because reducing the weight of the rocket means that it requires less fuel to reach the same altitude. This is not only more cost-effective, but also reduces the carbon footprint per launch, which is substantial in commercial aerospace. This coupler is a giant leap forward for SARP and will give the team more flexibility as it pushes onwards towards space.
Do it.
All right, nice work, SARP. All right, so for our next video, we have from the Society for the Exploration and Development of Space, a team that works on projects. Let's see it.
We are the Students for the Exploration and Development of Space, or SEDS at UW, a new chapter of the national organization composed of students from all different majors and all walks of life. We work on projects. Our current flagship project is the SEDS MultiStage Rocket, led by the 2021 ANA Capstone team. The SEDS MultiStage Rocket was originally aimed at competing in a regional rocketry competition that challenged students to launch a 1 kilogram scientific payload to an altitude of 10,000 feet, using only off-the-shelf motors. The competition has since been canceled due to COVID-19. However, the Capstone team has carried on in preparation for next year's competition. Reaching 10,000 feet has been done countless times before with a single stage, so why two? One of our team's fundamental goals is to learn as much as possible about our launch vehicle and to provide infrastructure for future generations of SED students looking to scale up and target much more ambitious altitude goals. To reach 10,000 feet and to meet competition requirements, our vehicle has incorporated some of the following into our design. A scientific payload that measures air pollution as a function of altitude, an accelerometer measuring the drag, and a strain gauge to monitor the vehicle's vibrations. We've included a lightweight structure made of carbon fiber that handles the compressive loads during flight with a factor of safety of 3. We have a cleverly designed 3D printed interstage coupler that houses avionics and our separation charges. We have a set of flight computers that handle staging, separation, and parachute deployment. And we also have a GPS in our nose cone for tracking. We also have a set of ripstop nylon parachutes, including a parachute for both the booster and sustainer stages, as well as a drogue parachute for the upper stage. Lastly, we have a set of ammonium perchlorate composite propellant motors that will propel the rocket to 10,000 feet. To ensure that our flight is a success, we have tested our materials, we have ran aerodynamics tests, we are planning on running vibrations tests on our payload and avionics, and we are planning on running a hot fire test to validate the thrust profile going into our trajectory analysis. We are currently in the process of manufacturing our airframes, electronics, and test stands. Despite COVID and despite multiple launch cancellations, we are carrying on to serve as the foundation for next year's competition. CEDS offers students from any major with any skill level the opportunity to apply core engineering principles on large-scale projects. Experience on such projects are invaluable in the growth and development of future engineers and space-loving humans. The ANA Capstone project is no exception. We are CEDS, and we work on projects. Ad astra per astra.
So awesome to see them working on projects. All right, nice job, everyone. Okay. It's a nice long credit screen. Nice work, Seds. Well, it was an amazing effort to see all the teams bring this creativity and honestly make the capstone process pretty fun. And it's really a real skill to be able to communicate these kinds of projects in 3 minutes. And it's also like invaluable to be able to show this kind of video to people who are interested in your project and give them a whole rundown, but without getting lost in the details. So nice work, everyone. So I'd like to thank everyone involved with the Capstone Film Fest here, in particular, Professor Christy Morganson and Kurosh Hadi. Thank you so much. I'd also like to thank the alumni judges panel, including Mike Taniguchi, Jim Teslo, Heather Ross, Rao Varanasi, Eleanor Forbes, Eduardo Gonzalez Vega, and Tob Thompson. So thank you all so much for participating in our Capstone Film Fest, and well, the whole Capstone process, really. And as well, also our industry sponsors, Aero Environment, Applewhite, Boeing, NASA, and of course, I'd like to thank all the Capstone teams. So that's it for this year. And remember to vote in the People's Choice Awards so we can find out which one was the best.